All right, ladies and gentlemen, welcome to another video going through my slides. This one talks about uniform circular motion. I've uploaded a link to a video that I've watched. I really like it. It's another description of uniform circular motion. I recommend that you check it out. It could be very helpful. Help you understand some of the stuff that you need to know. So, all right, let's go ahead and launch into this. So uniform circular motion means that the motion of an object is in a circle and it's traveling at a constant speed. Okay, we're not dealing with a rotating object right now. We're only looking at an object who is moving in a circle and it's moving at a constant speed. Velocity is a vector. All right, so why would I say constant speed, which is a scalar, instead of velocity, which is a vector? Well, the fact that velocity is a vector suggests that direction matters, all right? And if an object's moving in a circle, it's constantly changing direction, which means its velocity is constantly changing. So we can't claim that an object moving in a circle has a constant velocity. That's impossible. If it had a constant velocity, it would be going in a straight line, not a circle. So when we talk about uniform motion, we're talking about something that's moving in a circle and it has a constant speed. Now, I know this is labeled velocity. An object moving in a circle can have velocity. That's okay. It's just that velocity is not constant. That velocity is frequently and constantly changing. All right. So one complete circle, one complete revolution around a circle is going to be equal to 360 degrees or 2 pi radians. Okay, that's just something to remember. And something else to note is that when we talk about uniform circular motion, the word uniform means evenly distributed. Something remains the same size. It's not changing. All right. This word uniform is actually going to come back in other topics that we have talked about. Okay. So the velocity of an object in circular motion is going to be perpendicular to the direction of the motion. So if we look here, this image, the direction is counterclockwise, so our velocity always is perpendicular to the circle, but it's still somewhat in the same direction as the circular motion. All right. Now, even though the velocity is changing, when we claim uniform circular motion, that tends to suggest that the magnitude or size of the velocity remains constant. Notice that these arrows are all roughly about the same length, okay? The magnitude or size of the velocity stays the same, but because the direction is constantly changing, then we have to say that the velocity changes. So constant speed, constant magnitude of the velocity, all right? Now, I want you to consider these 3 questions. What's our regular definition of velocity? See if you can come up with an equation. What is the distance traveled by the object during one revolution? What do we call that distance? It has a specific name. Also, what do we call the time it takes, the amount of time it takes to complete one revolution? Just one. There's a specific word for that as well. So pause the video, think about it, look it up if you need to. So hopefully this is what you came up with or close to it. We have our regular velocity equation. Velocity is equal to displacement or a change in position divided by time. Notice that I'm using an S here. You could have used delta x, delta y. In this case, I chose to use a delta s. It's all referring to the same thing, and that's okay. All right, so this is our basic definition of velocity, basic equation. The distance for one revolution, that's just the circumference of the circle. You go around the circle one time, that total distance is the circumference, all right? The time it takes for one revolution, the time it takes for one complete cycle, you could say, we call that the period, all right? So circumference period along with our equation. Now, here's our basic equation. Instead of displacement, what we're going to do is we're going to replace that with the distance of one revolution, which is the circumference. And we're going to replace the time, with the time of one revolution, which is the period. All right, now circumference is 2 pi r, r being the radius. The period is represented by a capital T. So this equation right here, velocity equals 2 pi r divided by t. That is the velocity of constant magnitude, all right? So when we're looking at uniform circular motion, we're trying to figure out the velocity. that equation can help us determine the velocity. Not the direction, but just rather the magnitude of the velocity. All right? So let's talk about direction. It's going to be very difficult to use our traditional coordinate system. Normally, we treat up as positive, right as positive, down as negative, left as negative. That doesn't work so well here because our position, our direction is constantly changing. So it's going to be difficult to use that. All right. So what do you think could be a better solution, an easier way to describe the motion of an object when it's moving in a circle? Well, for this, we're going to refer to whether it's going clockwise or counterclockwise, okay? The unit circle is counterclockwise, so we consider counterclockwise to be the positive direction when it's in uniform circular motion. Positive direction is counterclockwise. Clockwise is the negative direction. Now, just like our traditional XY coordinate system, if we feel the need, it's going to make our life easier to change the coordinate system, go for it. But typically, we refer to counterclockwise as positive and clockwise as negative. Let's try to apply what we've learned, all right? So you're spinning a tennis ball on a string in a circle. We'll say it's a vertical circle, up, down, okay? And in the positive direction, all right? The string is 2 meters long, and it takes 40 seconds for this tennis ball to make 10 revolutions. What is the magnitude of the velocity of the tennis ball? Go back to the stuff we've talked about, look at our velocity equations, see what you can come up with. Pause the video if you need to. So the first thing I'm going to point out, the 40 seconds here, that is not the period. The period is the amount of time for one revolution. This time of 40 seconds is the amount of time for 10 revolutions. So you need to divide this, all right? You need to divide this. One period is going to equal right around 4 seconds, all right? Right around 4 seconds. When you put the radius into our 2 pi r divided by t, you should get a final answer of pi. Pi meters per second would be the magnitude of the velocity of the tennis ball, all right? Now here's what I want you to think about. Let's assume that the string suddenly snaps, okay? You're moving this tennis ball in a vertical circle, positive direction, and when the tennis ball gets to this point, the string suddenly snaps. I want you to describe the motion of the tennis ball. Now, before we launch into that, before you start that, just a few reminders, okay? Remember, motion is a description of several things. One, it describes the position of the object. It describes how that position changes, which is what we call displacement. Motion also describes the rate at which the position changes. That's what we call velocity. And then it also helps us understand the rate at which the velocity changes, which is what we call acceleration, all right? Now, to fully describe the motion of the tennis ball in this situation, I want you to address two things. I want you to give me an accurate description of the tennis ball. I want you to give me an accurate description of the direction, an accurate description of the direction that the tennis ball is going to travel after the string snaps. And the second thing is I want you to describe accurately what is going to happen to the tennis ball's rate of motion after the string snaps, okay? Think back to Newton's first law. That's going to be pretty helpful here, all right? Pause the video, think about it, see if you can describe it. Well, let's remember Newton's first law. An object at rest stays at rest. An object in motion stays in motion in a straight line at the same speed unless there's a non-zero net force acting on it, okay? So once this string snaps, there's nothing else. That string was the only thing that was making it go in a circle, all right? Since there's nothing making it go in a circle anymore, no forces causing it to go into a circle, this tennis ball would start moving in a straight line. The velocity at this point is straight up, so it's going to keep going straight up, all right? So its direction in this case would be straight up. But what about the rate at which it's traveling? Well, it's going straight up in the air. There is still the force of gravity pulling it down. That force of gravity is going to cause the velocity to slow down until the ball reaches a peak, and then it will start to come back towards the ground. But that one moment, that one instant, the first few seconds, the tennis ball is going to be going straight up, and it's going to be slowing down. Okay? All right. So here's a question. If an object's traveling in a circle at a constant speed, is the object accelerating? Well, what's our definition of acceleration? Well, acceleration is a change in velocity over a change in time. So remembering that, would an object moving in a circle at a constant speed, would an object that's experiencing uniform circular motion be accelerating? The correct answer is yes. It is going to be accelerating, all right? Because the direction of our velocity is always changing, that means that the velocity is always changing. And the acceleration is simply the rate at which the velocity changes, all right? So yes, it is accelerating, and we have a special word to describe the direction of this acceleration. The word we're going to describe is centripetal, all right? The word centripetal means center seeking. It is an adjective that describes a vector. All right, we can use this adjective to describe a vector and help us better understand the direction that this vector is experiencing. Okay, so an acceleration, all right, we're going to apply this to a lot of different things, but an acceleration is seeking the center. All right, it is a centripetal thing, centripetal acceleration. So, quick review. Let's see if we can remember what happens when we have acceleration and velocity in the same direction. If acceleration and velocity are going in the same direction, what happens? Likewise, if the acceleration and the velocity are going in opposite directions, what happens? Well, when the acceleration and velocity are in the same direction as we have in this image right up here, if the acceleration and the velocity are in the same direction, it's going to speed up. Doesn't matter if they're both going in the positive direction or they're both going in the negative direction. They will speed up. If the acceleration and the velocity are in opposite directions, one's positive, one's negative, then the object is going to slow down. Okay? Now here's my question, new question. What happens if the acceleration is perpendicular to the velocity? If we look at our circle, our acceleration is centripetal, it's towards the center. Our velocity is tangent or perpendicular to the circle itself, which means that our velocity and our acceleration form a right angle. They're perpendicular to each other. So what kind of an effect is going to occur when the acceleration is perpendicular to the velocity? Well, the magnitude or size of the velocity or the speed will not change. It will continue to move at the same speed, same size of the velocity. However, it will change the direction. All right? So, hence, we will have constant speed or the constant magnitude of the velocity, but the direction is always changing because our acceleration is always causing it to move in a circle. It's always seeking the center, always perpendicular to our velocity. All right, here's an equation for you. We can calculate centripetal acceleration with this equation. You need to know this equation, all right? Centripetal acceleration is equal to your velocity squared divided by r, all right? Divided by r. So let's practice. A 100 kilogram car is moving at half a meter per second. It takes a turn around a circle in the clockwise direction, and that circle has a radius of 5 meters. I want you to determine the acceleration of the car. Don't forget to describe the direction. Pause the video, see if you can figure this out. Use all the stuff that we've gone over so far. All right. You should have gotten an answer of 0.05 meters per second squared. So here's our basic equation. We have our velocity that we put in here, square it, divide that by the radius of the circle, and you will get 0.05 meters per second squared. And that acceleration is always centripetal. It is towards the center of the circle. All right? All right. Let's start bringing this together with dynamics, what we talked about last time. What is Newton's second law? And then I want you to think about this question. Is there a force acting on an object that's traveling in a circle? Doesn't matter doesn't matter what object. If an object's moving in a circle, is there going to be a force acting on that object that's traveling in a circle? What do you think? Well, first off, let's answer the first one. Newton's second law, force equals mass times acceleration. Technically, the sum of the forces, the net force equals mass times acceleration. To keep it simple, we're going to look at just one force acting on an object. So it's just one force equals mass times acceleration, all right? If an object's moving in a circle, there is a force acting on it. Guaranteed, okay? In order for an object to accelerate, there has to be a force that's causing that acceleration. Therefore, if an object's traveling in a circle, there has to be an acceleration. And if there has to be an acceleration, there has to be a force acting on it, okay? So anytime we're dealing with uniform circular motion, there is always an acceleration, it's always towards the center, and there's always a force acting on it. Now remember, centripetal is an adjective. We are not describing a new type of force. Centripetal force can be any type of force. All it tells us is that the direction of this force is always towards the center. It's telling us the direction. That's it. All right? So, I guess I kind of just answered this one. If the direction of centripetal acceleration is towards the center of the circle, what direction will the centripetal force be? Well, it's going to be towards the center of the circle, okay? The direction of the force acting on an object is always going to be the same direction as the acceleration of that object as well. All right. Let's think about our tennis ball example. Okay, it's being swung on a string in a vertical motion. What is the main force that keeps the tennis ball traveling in a circle? All right. And I want you to tell me what direction that force is. So pause it if you need to. Identify what the force is, the type of force that keeps the ball moving in a circle, and then describe what direction that force is going to be. All right, well, tension is the main force in this case, okay? Now, if this is being spun in a circle, a vertical circle, gravity is also going to be helping out as well. But if it's a horizontal circle, then the only force that's causing the ball to move in a circle would be tension. Now, that tension force is going to be always directed towards the center. Therefore, we can claim that tension in this situation is a centripetal force. All right? Notice, centripetal is not a new type of force. It simply describes other types of forces that already exist. In this case, tension is a centripetal force. All right, here's a new situation. Consider the Earth's orbit around the sun, okay? We can assume that it's a circular motion. What would be the centripetal force that's acting on the Earth? Well, if you stop to think about it, the force that's causing it to go around the Earth, the force that's causing the Earth to go around the sun is the sun's force of gravity. And no matter where the Earth is in its orbit, that force is always directed back towards the sun or the center of the circle. Therefore, the centripetal force would be gravity. Gravity is the centripetal force. All right, how about this? Think about a car that's driving in a circle. What would be the centripetal force that's acting on the car that lets it travel in a circle? Well, as the car tries to turn, it's going to want to keep going in a straight line. And there's one thing that stops it. That is friction. If anybody has ever been driving on a very wet and slick road or on ice, there's little to no friction. You can't turn if there's no friction. Friction is the force that is required for a car to turn. So if a car is going in a circle, then in this case, that friction force that allows it to turn in a circle is going to be directed towards the center. It is the centripetal force. All right. Now, let's go back to Newton's second law. Force equals mass times acceleration. If we want to use Newton's second law for centripetal motion or uniform circular motion, then we simply need to replace our acceleration with centripetal acceleration. Because if our acceleration is centripetal, our force will be centripetal as well. All right. So take our equation, look it up if you need to. If we take our equation for centripetal acceleration and we put it into this equation, do a substitution, this is your centripetal force equation that you get, all right? Newton's second law applied to uniform circular motion. Mass equals velocity squared divided by r, all right? So take a look at this. First off, brace yourself. God, that's just not pleasant, but it makes me laugh at the same time. A 5-kilogram ball is connected to a strong rope and is spun in a circle at a velocity of 2 meters per second. The rope is half a meter long. I want you to first identify the name of the centripetal force. What type of force is it? Then I want you to actually calculate the value of that centripetal force. Pause the video, work it out, and then resume when you're ready to get the answer. So, since the ball is attached to a rope, and it's the rope that's causing it to go in a circle, then that tension force that's in the rope is what's causing the centripetal acceleration. Therefore, tension is the centripetal force, all right? So, if we take our centripetal force equation right here, and we input all of our known values, do the math, you're going to come out to get 40 newtons. That's the value of your centripetal force, and it is towards the center because tension is a centripetal force in this situation. All right, so a tennis ball is attached to a string and swung again in a vertical circle. Let's construct a force diagram, a free body diagram of the tennis ball when it is at the bottom of the circle, okay? So it's being swung in a circle. I want you to construct a force diagram for the tennis ball when it is at the bottom of the circle, okay? See what you can come up with. Fortunately, there's not too many forces acting on it, all right? We have two forces, the tension and the force of gravity. Now, tension is centripetal in this case. It is always towards the center. So at the very bottom, the tension force will be straight up. However, the force of gravity on a small scale like this is always down. So our force diagram will look something like this, okay? I'm not going to tell you how to do the top part, but I want you to think about what would a force diagram look for the tennis ball? What would it look like when it's at the top of the circle? See if you can come up with one. What if it's at the side? Exactly at a right angle of the circle? What would a force diagram look like in that situation? Okay, see what you can come up with. I'm not going to show you the answers right now, but it'd be a good little exercise for you. Okay, right here we have, looks like that video is not working very well. Anyhow, there was a video. I'll double check my slides to make sure the link's not broken. If it is, I'll go ahead and fix it. But in this video, somebody runs a loop. All right. The purpose of it in watching this is to look at centripetal acceleration and centripetal forces. I'm going to go to the next slide because I have a picture of it. So this guy in this video would run up the loop. He would run all the way and he would come all the way down. So I guess he came in this way and he ran all the way up and all the way around. And you have to be going fast enough in order for that to work. Otherwise, you won't be able to go into a circle. So let's analyze all the forces that's acting on this person as he runs through the loop. Start by constructing a force diagram for the person, and I want you to do it for when he's at the top of the loop, okay? Force diagram for when he's at the top of the loop. Okay. Hopefully you got this. All right. Should look like this, okay? Notice that we have the normal force. I guess if we go back to the picture, the normal force, he's pressing up with his feet, which means that this, even though he's upside down and there's nothing underneath him, because his feet are still pressing against the surface of the loop is pressing back against him and supporting him. Therefore, it would be a normal force. And then, as always, we have the force of gravity pulling him down. All right? Now, let's say that the loop has a radius of 4 meters and that the person running has a mass of 100 kilogram and he's moving at 8 meters per second. I want you to calculate the magnitude of the normal force. at the top of this loop, okay? Now, this is connecting circular motion with what we've already talked about with dynamics. I want you to go back and use those main, I think there are 5 dynamic steps to solve this, okay? This is a dynamics and circular motion problem. And try to also think about, where is centripetal acceleration fitting in? Where would we use centripetal acceleration in those 5 main dynamics steps, okay? If you've forgotten, maybe pause the video, bring up the dynamic slides, look through them, but see what you can come up with, all right? This one's difficult, but you can do it. All right. So we've already done step 1. We've got a force diagram. Since everything is in a single direction, we can skip steps 2 and 3. We're going to jump straight to step 4 here, okay? So here is Newton's second law. Notice we're using a centripetal acceleration because when he is at the top of the loop, his acceleration is going to be straight down, and that's towards the center. Therefore, his acceleration is centripetal, all right? So our net force, the total amount of forces needs to equal his mass times the centripetal acceleration. So our normal force, in this case, let's say that down is positive. We're going to redefine our coordinate system here. We're going to call down positive, all right? So in this case, since down is positive, the normal force is in the positive direction. Our force of gravity is in the positive direction, and our centripetal acceleration is also in the positive direction. Makes my life a little bit easier, okay? So your equation should look like this, and then you solve for the normal force to get to this point, all right? Now, all you have to do is plug in the numbers. Once you plug in the numbers, you should get a total answer of 600 newtons. 600 newtons. All right? Okay. Well, ladies and gentlemen, to be honest, this video is a lot shorter than my other ones because that's it. We've covered all of the basics for uniform circular motion. We hit on the velocity equation for uniform circular motion. We hit on what centripetal acceleration is, what the equation is for that, and we've applied it to Newton's second law and talked about centripetal force. All right, so I will go ahead and in AP Classroom unlock and upload some progress assignments that you can look at for a review to try and see how well you understand this. Ladies and gentlemen, don't forget that completing those, I'm going to check them this week, get it updated in the grade book, but completing those assignments in AP Classroom can increase your grade in this class. I will give you credit for that, all right? Also, watching this video, go into Google Classroom and actually say that you watched it, all right? Mark the slide appropriately so that you can get credit for that as well. All right, if you got any questions, let me know. Otherwise, go ahead and just keep reviewing, keep getting ready. Have a good one.